the mask.
Oh,
Thank you.
sorry.
No, it's okay. I'm just kidding. All right. So yeah, I'm back in my office. Huh? Not the real one though.
Ta-da!
No, in my office in my house. I'm not on the couch anymore, which is a big event for me. Big event. Uh, really a couch. I became like a real huge couch potato. Except, yeah, the potato part. But all right, so let's move on. We have a very special topic, and this topic is how important is
Of
it?
resonance.
How important is it? How
Very important.
Very, very important. That's right. Yeah, it is very important. And so that's what we're talking about. So again, we're gonna, unfortunately, I so far I've been going kind of at a reasonable pace. I don't know if it's too fast, too slow, too slow. I thought it was pretty reasonable. We have this lab that we have all this excellent, I mean, it's amazing lab, by the way. Oh my God. Ekin did such a fantastic job on it. You should be, lucky to have that kind of lab. It's just unbelievable. So I had so much fun going and coding the pause sequence. I went through it. It's just phenomenal, and you learn so much just by doing this. So I'm excited for you to have the opportunity to actually go through this lab. Because most people actually study MR. Actually there's no labs usually. They don't do any labs. I think it's one of the only places that this is actually done. So it's going to be fantastic. But we really need to cover certain topics like spin echo and T2 star and that kind of stuff. So we'll have to go over it. Otherwise, you go through the lab and you're like, well, I don't know what it is. Oh yeah, but there was this thing that I moved my responsibility to you. You have to read chapter 7. Read chapter 7. Ekin, there's tomorrow already labs, right?
Yeah,
Can we
there's
release?
two.
Can we release Did we release already the transcript?
The PDF soon. It's not finalized still, but I think in a few hours it should be. So yeah.
Okay. Make sure you read it also before that.
Yeah, if you can, that would be great.
Yeah. Apologize. It's been going through several iteration, and now it's just, oh my God, so great, so great. Let's see, share screen. Okay. Can everybody see? Okay. But it's important also if you to read, please read, if we don't get to this, really read chapter 7, and in particular read spin echo. It's really important. And T2 star, what are these? Otherwise you'll have you won't appreciate what's actually happening. Okay, so please do that. Okay, so where were we? Oh yeah, so we talked about the macroscopic effects of off resonance. And I said there's a few problem areas like the brain. Above every time you have air tissue interface, that's a real issue. Air tissue interface, that's where you have big susceptibility differences between the different tissues. And so that's where you'll see a lot of effects of changes in magnetic field. And I just showed you this example of a brain, and this is the map taken from some paper that they mapped the field map in the brain. So this basically this map at every pixel represents what is the field, the off resonance field with respect to the main magnetic field. And we're talking here at 1.5 Tesla. So at 3 Tesla, it will be doubled usually. So the effect at 3 Tesla is much more significant the effect at 7 Tesla would be 7 over 1.5 times. So really, really, really bad effect. And you can see that definitely next to the sinuses, you have big inhomogeneity. And look at the ears. This is where the ears are. At least I have ears in this area, and you can see kind of there's a change in field next to the ears because of the ear canal. Okay. Then of course there's a macroscopic effect. You know, you've seen metal artifacts and all that stuff. So these are also big effects, and that's because of the susceptibility differences between the metal and the tissue. But there's also microscopic effects. So here's an example in the lungs. The lungs have approximately like 1/6 composed of 1/6 tissue and 5/6 air. So it's pretty, you know, it's pretty airy. And if you look actually inside the lung, you have, you know, it's water and tissue. So, but you have tissue and you have air, and it's just they all touch each other in a very small area. So the result of this is that you have a distribution of field and frequencies within the lung that affects it significantly. So if you look at water at at body temperature and air, water will be minus 9.05 ppm and air would be 0.36. And then the lungs are, the susceptibility is really a distribution. It's the distribution around minus 6 ppm, but it's very, very broad because of all these interfaces that create a lot of very interesting effects. But what is interesting about susceptibility, that it really tells you a lot about the microstructure. The fact that there are these susceptibility differences, then it can tell you a lot about what is the tissue is built from. So there's a whole field that is called quantitative susceptibility mapping, where you actually try to map the susceptibility within the body, and that can tell you a lot of things. For example, you can image then calcification. You can look at veins. We'll talk more about that in a second. So there's a lot of information that's embedded that tells you about the microscopic structure of tissue. So even though your imaging may be at 1 millimeter resolution, 3 millimeter resolution, the fact that you're getting certain signals that decay a certain amount tells you a lot of what's happening at a micro scale. Okay, so that's the beauty about MR, that it lets you also probe the micro scale. Blood is a huge source of susceptibility too. Remember, water is minus 9.05, but hemoglobin molecule, when it's without the oxygen, has a susceptibility of 0.15. So this is deoxyhemoglobin, hemoglobin without the oxygen attached to it. When hemoglobin is inside blood cells, again, it's a combination of tissue, water, hemoglobin together. Then the susceptibility is around minus 6.52. So closer towards water, but because hemoglobin, it's pretty big molecule inside. There's a lot of hemoglobin inside red blood cells. So this is why the susceptibility is that. And then because there's also plasma, right? Plasma inside blood. So if you actually look at the oxygenated blood, then susceptibility is around minus 8.77. Now, what's interesting is that once oxygen is bounds itself to the hemoglobin molecule, then the susceptibility of blood becomes pretty much the similar susceptibility as the rest of the tissue. So there's a change in susceptibility between oxygenated and deoxygenated blood, which is pretty much amazing, right? Like if you think about it, well, it's not amazing, it's a fact, but what you do with it, it's amazing. So there's actually a beautiful paper. It's called, I told you about this, right? It's a review paper by John Schenck, Role of Susceptibility in MRI. It's just a fantastic, fantastic paper. And I really, really recommend you reading it. So all the information is taken from this paper. Okay, so am I going to talk about? Yeah, okay, so I'll talk, you'll see in a second kind of where I'm leading to. I hope so, if I actually, I feel like I'm missing a slide here. No, I'm okay. There you go. Okay, so the other source of inhomogeneity, magnetic field. So we talked about susceptibility both in the macro scale, the micro scale, as a source of inhomogeneity. Now let's talk about chemical shift. So protons in complex molecules are in fact shielded or protected from the magnetic field by adjacent spins and electrons. So effectively what you have is some factor sigma, which is the shielding constant that depends on the molecular structure, what it does is that if you actually have a certain field that is applied on the tissue, then because of this effect, the effective field that the proton will see will be different. It will be different by sigma. Okay, so it could be a very small effect, but it is very visual. So, for example, lipids have this molecular structure. You know, there's a carbon, how do you call it, backbone. There's a carbon backbone that is connected, and then you have hydrogen atoms that are attached to it, and it really depends on the type of lipids, whether you have double bonds or you don't have double bonds, and so on and so forth. But what you see is that if you actually look at the NMR spectrum, the NMR spectrum of lipid looks something like this. So it's all with reference to TMS. I think I told you about this before. I forget what the name of, it's pretty long name for this molecule, but the reason that they always compare against this molecule is because it's independent. It doesn't exhibit change in its resonance frequency with temperature. Okay, while water, yeah, tetramethyl sulfate. Yeah, probably, I think so. But it doesn't exhibit any change in resonance frequency with temperature, so it's stable. That is not true for water. Lipids change a little bit, but water actually changed quite a bit, which is, by the way, used to do thermometry. All right, so if you look at this, then you can see that there's really a main peak at around 1.3 ppm. Now, by the way, this is positive, and it's interesting why this direction is positive. Do you have an idea? How old is the field of NMR? It's pretty old. So when they used to print spectrum, it was like a roll that would go. And because it was a roll that would go, then actually it would print it this way. Anyway, you would print first 0 and then positive, and then the roll would move. And this is why, really in chemistry, they would they write it in this direction. Anyway, you see a big peak at 1.3. That is the CH2. So there's a lot of CH2 in lipids. So that is the main peak. And of course, there's also CH and CH3. And so each of these will have different chemical shift. CH will be actually closer to water. So it's about, I don't know, less than 1 ppm from water. And then CH3 and CH2 are pretty far away. So, so lipids from CH2 is about 3.4 ppm below water. And at 3 Tesla, it's around 440 hertz difference. 440 hertz difference at 3T. That is quite a bit of inhomogeneity if you think about it. And so there's going to be consequences because of that. So yeah, this is actually a real spectrum of water, of lipids that you can actually see. And there's actually 1, 2, 3, 4, 5, 6 peaks corresponding to various neighborhoods and some of the hydrogen with respect to where they are with carbon, with respect to other hydrogen, and so on and so forth. Okay. So the thing is, okay, so we have susceptibility, we have magnetic field homogeneity, we have chemical shift, but tissue is really heterogeneous. So tissue is really a combination of all of these, the chemical shift, susceptibility, and also the different geometries, right? We said susceptibility also depends on the geometry. So the results are very complex in terms of what happens. So interesting cases are the blood, which is used for FMRI. So susceptibility changes in the blood are used to do functional brain imaging. We'll talk about that a little bit. In the lungs, it's fascinating what's going on. Tubercular bone. Tubercular bone, do you know what it's made of? So have you ever seen pictures of tubercular? It's amazing. It's like very small structure, very small structure. I'll try to pull out some things for you for next time. Very fine structure of calcium, and between them there's a lot of fat actually inside the bone. So the bone is it's kind of a mix of calcium and fat altogether. So there's a lot of susceptibility and chemical shift inside the bone. There's actually a lot of studies that are done that try to exploit this kind of microstructure in order to understand, osteoporosis and all sorts of bone disease and so on and so forth. And of course, iron deposition both in the brain and the liver, a huge problem, especially for males and male children. Where it's very hard to get rid of iron. So one of the ways to actually image iron concentration is using MRI. So there's a big program, by the way, at the Oakland Children's Hospital to do that. Now, what are the effects of susceptibility or magnetic and all these magnetic field homogeneity on imaging? First of all, there will be some effect on the magnitude of the image. There are effects on the phase of the image. Okay, now it's this is kind of the first time we start talking about like where the phase comes from. Well, the phase actually comes a lot from chemical shift. You'll see that there's also effect on the geometry. So you're making an image, but because of susceptibility or because of magnetic field homogeneity, the geometry of the image that comes out is going to be different than the actual geometry. And you can kind of see how this could be a problem. Let's say you're doing a scan in order to do a pre-surgical scan, where you try to figure out where things are, so that when they do the intervention, they'll go and they maybe put the needle to the right place, but now there's some geometrical distortion, maybe a centimeter displacement, and that is a real problem, because then you're not going to hit the right place. And the last one is blurring. So and we've seen some of this effects right before. We've seen with T2 we've seen a magnitude effect, and then we've seen a blurring effect, right? Remember last time, Tuesday, not far ago, right? Like if you even if you didn't sleep, your short-term memory still should work, So yeah, so it was magnitude and blurring. Now with susceptibility and with magnetic field homogeneity, phase and geometric issues. They all depend, by the way, on the spatial scale that we look at and the type of acquisition that you do. And what do I mean even by scale? For example, if I just excite them, like I put a head inside the magnet, I perform an excitation, no encoding whatsoever, and I look at the FID, the free induction decay. Well, that's a very That's a very large scale. It looks at the entire brain as a single voxel, effectively, right? The entire head. Now I start performing encoding, let's say 3mm resolution. I'll see some different effect. Then I will image at 1mm resolution, or at, let's say, 100 microns. So the effect that you see will depend on the scale, on the size of the voxel that you image. And of course, it will depend on the acquisition strategy. If you image very fast, the readout very fast with strong gradients, you might not be as susceptible to this issue. But if you have very long readouts, then of course, the fact that spins process at very different frequencies than you expect are going to have issues. Okay, so let's see what the effect on the free induction decay, on the FID. This experiment is called pulse acquire. Guess what? In the lab, you're going to do a pulse acquire experiment. You're going to put a phantom in, and you're going to apply an RF pulse, 90-degree RF pulse. And if the signal is on resonance, you would expect it to decay with E minus T over T2, right? You would expect something like this, right? If it's on resonance. Signal that decays, okay? What would happen if it was a little bit off resonance with respect to the field? Let's say, what if that spin was a little bit off resonance, or that, volume, but still uniform, How would the FID look like? What did you say with your hand, Anita?
Yes, it wouldn't get demodulated quite right. So maybe it would still have some cosine.
That's right. That's right. It would not be modulated just right. And so it might, this would be then the envelope, right? And this would be the real part. And then, of course, you'll have an imaginary part too. Okay. And so you see oscillation. Okay, so it will, and basically the envelope will be the T2. Okay, so it would look like this. This is exactly what you'll see in the scanner. Okay, all right. So the signal will decay with T2. All right, this is what's called a simple spectroscopy experiment. Now, with susceptibility variation within the volume, okay, so now you have a volume, but there is field inhomogeneity within the volume, okay? You apply, and look what happens. This was T2. But instead, your signal decays much faster than you expect. And the question is, why? Why it decays that way? Why? Any thoughts?
Maybe different elements in the volume would have like a different phase and would cancel each other out.
12 points. Very good, Daniel. Fantastic. Absolutely. So that's actually what would happen. There's going to be dephasing that will happen. Not all the spins will process at all the right frequency, and so you'll get some cancellation that happens. And so the signal will decay much more rapidly than you expect. Okay. So the field that we have is a function of space. Okay. So our field is a function of space, and you can decompose it into a field that is uniform and then an error field. Any deviation from this uniform field, and the error field is a function of space. Well, B0, of course, is constant throughout space. Okay. So this error field, of course, is a contribution of, again, all those things: chemical shift, magnetic field inhomogeneity, geometry, and susceptibility. Okay. So we're gonna try to use that in order to derive what would be the phenomena. Okay. So The error are both spatial and spectral. That means that you got different spectra, different frequencies at different positions. Okay. So in the rotating frame, the effective field will only be the error field, right? Because if we're talking now about the rotating frame, in the rotating frame, we're already assuming that we're rotating at omega 0, which is correspond to the main magnetic field. So now we can remove its effect. And the effect that is left now is some error field that is pointing in the function that is actually space dependent, pointing in the z direction or k direction. Okay. That means that I'm going to have also a distribution of omegas or frequencies that will be also a function of space. So omega sub e of r is gamma e of r, or if we actually look in hertz or megahertz or so on and so forth, then we just divide that by 2 pi. Okay. So we don't know what it is, but it's just, you know, it could be random, it could be not. I mean, it could be various distribution. Okay. So now let's now try to analyze what will be then the signal that we get, right? Like what do we have? So our magnetization mxy, I don't have a gray here, but let me erase this. Mxy at position r at time t is the magnetization mxy at position r in time 0 that decays with T2. Okay, we've seen that, right? Decays with T2, but it also processes according to this field, right? According to the applied field or the distribution of resonance frequencies. So a spin at some position R will have its magnetization mxy r, and then it will have some precession that's going on. At what frequency? Well, so the precession will be e minus I omega error of r times t. Okay, so spins over time will start accruing phase according to this angular frequency. Okay. Now, we've seen this before. Where did we see something like this before? That you have something that depends on r times t. Depends on r, yeah, and something times that. And with I times something r. Where did we see this before?
Gradient.
Gradients. That's right, gradients. Guess what? Gradients are also a source of magnetic field inhomogeneity, only that one is intentional. Spins, when you apply a gradient, process the different frequencies versus space. Now, spins do exactly a similar thing. That's a weird sentence. Exactly a similar thing. But do a similar thing. I'll just delete exactly. Do a similar thing where they, in different places in space, they process a different frequency, but it's not a linear function. Okay, it's very wacky function. And it doesn't have to be even continuous if you have chemical shift. Okay. So the received signal is the integral of this entire volume. Entire volume of this thing. Okay, mxy r0, and we integrate over the entire volume. Now this is the magnetization that we excited. This is the relaxation. And as it turns out, this is actually dephasing. This causes dephasing. Different spins at different positions will have accrue different phase. So there will be a phase dispersion that causes the signal cancellations and loss. All right. So here's kind of a situation. I excite, and now I'm showing you what's called the isochromats. So different, let's say I excite, and now each one of those arrows represent some spins in the volume, and based on their color, they have they observe a slightly different field, and so they resonate, they process at slightly different frequency. So you excite, and then immediately after excitation, you start getting a spread. Okay, so you excite, and the signal immediately after excitation is going to be the sum of all of these, right? Of the the sum of all the transverse components. So it's going to be kind of this vector over here. So this vector over here will have some projection onto the XY plane, and will have some signal. Now, after some time, those spins start dephasing, and this vector, when you try to average, then it gets closer to the main axis. So now its projection is going to be smaller. So now this will be the signal. And then once the spins are just completely dephased, then they all cancel each other, and they're basically no MXY component, even though there's tons of MXY components, right? Each of these spins have MXY components, but their signal cancel each other. Does that make sense? Any questions? I'll let you watch this video one more time. All right. Okay. So effectively, if this is my volume, okay, and the reason I do it, why did I draw it in blue?
Because of water.
Yeah. Okay, so the signal comes actually from the entire volume. These are fish. I don't know if I'm not very good at drawing. If you didn't know. So they swim in the water. Okay, signal comes from the entire volume. Okay, so if you actually ignore right now any inhomogeneity, let's say the volume is homogeneous, the signal that would come down is something like this and decays with E minus T2, T over T2. Okay. Now, if there is inhomogeneity here, then now the signal would decay. Hold on, did I? Oh, what's going on here? Ah. Sorry about that. Okay, so yeah, so now I want to understand kind of what are the off-resonance effect on the FID, right? So I get mixed here some. I don't know what's going on. All right, never mind. But let's just focus. So first of all, you get inhomogeneity that will result in signal loss. We'll understand that it's come to known as being T2 star, and I'll explain in a second what does mean. So effectively, there is some decay here, and that decay is often approximated as decay with a slightly different T2, which is not really T2, that's why we call it T2 star, but you can kind of see that it's not really exponential. It's just approximated as an exponential. It could actually do all sorts of things like this when, they can cancel, and then, some of it done as a cancel and cancels again and all that stuff as they dephase. So with inhomogeneous B0, then you get this type of an effect. Okay, but we often model this as exponential decay. Whether that's a good model or not, that depends on the scale that you image. Now, when you apply a gradient, that's also a source of inhomogeneity. And of course, spins will start precessing and will start dephasing. And of course, you'll see signal decay. Now, if you have a homogeneous volume, let's say a square volume, when you put a gradient, what will be your signal? When you have a gradient and it's a square volume, and then you put a gradient on, what will be the FID? I told you to tattoo this shape. It's a shape worth tattooing.
It's a sink.
It's a sink. Yeah, it will be a sink. Yeah, absolutely. So the signal will decay like a sink. And of course, the sinks decay, sinks decay eventually. So you have to understand that this dephasing, it's sometimes we think about it as, oh, loss of signal. Sometimes we think of it as the signal. It's just like, you have to, it depends on the context. Of course, this is not going to be exponential, right? Even though it's, it's very strong in homogeneity, it's not going to be exponential. But we can sometimes approximate it exponential, right? So with the gradients, you have this, you have this decay. And this is a very similar thing that happens here, except here it's non-uniform, and so it's slightly different. Okay, so gradients are a very strong source of this inhomogeneity. Inhomogeneity results in the signal loss that is known as T2 star. I'll explain what T2 star is. And it's approximated as exponential. So the signal that you get in a voxel, okay? Signal in a voxel. So this is a line, and just like signal in a voxel is the following: is the integral over the voxel of mxy r0 e to the minus I error frequency times t e to the minus t over t2. T2, by the way, is also a function of r, and then dr, right? So the integration of the entire voxel. Okay. Now we have two decay components, right? Like there's two things that are happening. First of all, there's the integral, and then there's this thing, and then there's this thing. So what we do is we say, you know what? It's really complex. Let's try to just approximate this as a simpler function. And that function is just an integral over the voxel. And then decay, and then you multiply by E minus T over some T2 star, which whatever, that thing is. But it's just a value that you can then approximate this function. And basically approximating this function means, that I take and I fit an exponential to this thing, or I fit an exponential to this thing, right? I can, it's going to be approximate. That's okay, right? People do this all the time. Now, this T2 star that you get is actually a combination of two things. It's a combination of this inhomogeneity, and it's a combination of the real T2, the real parameter, relaxation parameter of the spins. So effectively, what we do is we say, 1 over T2 star equals 1 over T2 plus 1 over T2 prime. This is the real T2, which, by the way, it's also a fudge factor a little bit, but let's ignore it now that it's a little bit fudgy. Plus a component that it depends on the dephasing part. This is relaxation and this is dephasing, okay? And sometimes it's also described as R2 star, which pretty much is the inverse of this. And in that case, R2 star equals to R2 plus R2 prime, okay? So the result of dephasing is really this, but we put T2 and T2 star and T2 and T2 prime into the mix, and we say, you know what, let's call you T2 star. Okay. Now, T2 star is not a great model for large scale variations. For example, dephasing near the sinuses and stuff, if you try to fit an exponential, it's not a good fit. But it's a fabulous model for small scale distribution variation. For example, dephasing near capillaries, dephasing in the lungs, this is actually a pretty good model for it. Okay. Any questions? Oh, I'm getting to one of my favorite parts. So, I don't want to, delay and, but I'll pause for at least, a question. No question.
Yeah, I have a question. Could you go back to the previous slide, please? So, or maybe one before that. Never mind. So the question is, you said that gradients are a major source of inhomogeneity.
Yep.
So I was just
But you
wondering.
apply.
Yeah, I know. But so I'm wondering about the terminology, because usually when we say field inhomogeneity, we don't mean gradients, right? We mean.
No, we don't. But my point is that it's effectively the same thing, except that gradients are inhomogeneity that we can control. There are some inhomogeneities that we cannot control. Gradients is homogeneities that we can control. But the effect of applying a gradient or field homogeneity within a voxel are very similar to each other. Okay, the effect. And
Yeah,
that's
that makes
why we have a thing called a crusher, which we will talk about when we do imaging, that effectively use a gradient to dephase the spins and get rid of the signal. Okay, that's something that people do all the time. Okay, and we'll talk about that.
Thanks.
Okay, so gradients act kind of like as a T2 star source. This actually, no, we're talking about right now. We're talking about right now, Efrat, about the crushers. I forgot. So gradients acts as a T2 star source. So if we have a voxel, and the reason this voxel is in blue is because it's filled with water. I apply an RF pulse, I apply a gradient, and that kills the magnetization. I will get no signal after it's done, right? I will put a lot of cycles of phase within a voxel, and so the signal from the spins will just disappear. In a very similar way, if I have a voxel that has blood capillaries inside, and let's say this is deoxygenated blood. Deoxygenated blood has susceptibility difference with respect to to the rest of the tissue, and so it will actually induce field variation that is a result of looks something like this. And so spins within the volume will start processing at different frequencies, and you'll get exactly the same result. You excite RF, and then it will decay. And it will decay faster than you would expect because of all these inhomogeneities. Because if I have a spin over here, and I'll have a spin over here, and I have a spin over here, and I have a spin over here, they all see a different field. And so they'll start dephasing. All right? So now I'm gonna play you the song.
Sealed by an inhomogeneous field. Twinkle, twinkle, T2 star. Something pulls those spins apart. Now I know just what you want. Twinkle, twinkle, T2 star, how I wonder what you are. XY signal soon decays. Why do spins go out of phase? Twinkle, twinkle, T2 star, something pulls those spins apart. XY signal soon decays. Why do spins go out of phase? Twinkle, twinkle, T2 star, now I know just what you are.
This band is called Science Groove, and they have pretty cool songs. Canadians, of course, because only Canadians can be so nice. So I hope all of you kind of now know the notion of T2 star. But I want to show you an example of the FMRI. So FMRI, you have two situations, and I'm kind of simplifying a lot of things over here, all right? So this is really simplistic models. And I'm saying that because I know there's some people who do FMRI here and don't want them to, you know. All right, so the simplistic model of FMRI is that at rest, when there's no activation, then you have a higher concentration of deoxygenated blood. And where there's activation, there's low concentration of deoxygenated blood. Okay, so more blood, basically oxygenated blood. So between these two cases, if you have, let's say, so if you have neurons firing, what would happen is that they would use the oxygen, but as it turns out, actually, that the brain kind of tries to overcompensate and brings more blood to this area. So actually, the level of oxygen increases. But there are modulation of level of oxygens when there is activation. And so in the case of rest, you will have some field of homogeneity, and when there's activation, there will be no field of homogeneity. And now what you do is, in order to image this difference, then if you actually look at the dynamics, so as spins process, so after a certain amount of milliseconds, you'll be able to see some differences between these two populations, right? Like whether it is activated or not. So let's say now you excite, and now you wait about 40 milliseconds or so, then you see that there is a difference between these two populations of certain, like some percent. And so what is often done in MRI is that you collect images at around 40 milliseconds after excitation, and then you continuously collect many images and many images. So whenever you have activity, your signal is going to be a little bit higher, and then whenever there is there's less activity, then the signal is going to be a little bit lower. So the result will be fluctuation in your signal you'll be able to see across images. Okay. And I have to say, this is one of the most amazing things that you can, I mean, like, just think about it. This is a moment. It's one of those moments that you have to stop and go like, all right, well, there's this nuclear spin, it interacts with magnetic field, it emits, it processes, emits radio frequency. Yeah, that's great, then you have blood and hemoglobin and changes in magnetic field and all that stuff. And then there's brain activity, neuroscience, body regulates blood and all that stuff. And ultimately you're able to actually image brain function using MRI, using this like nuclear spin, like the tiniest thing almost the tiniest thing in the universe. Hydrogen nuclei. You're able to sense, using this tiniest thing, brain activity. That's a moment, okay? It's a moment. All right. Okay, are we doing on time? We have half an hour, that's good. All right, so now we understand at least this T2 star component, right? The signal cancellation. Now let's try to see what is the effect of off resonance on the imaging. Okay. All right. So we're going to do something very similar to what we did with T2. Now that we have T2 star model, then we can basically leverage the same thing, right? Like the same analysis that we did with T2, in order to do this. Otherwise, it would be very difficult. But now it's much easier because we define just another decay component. Okay. So effectively, when we do, let's say, a 2DFT sequence or a spin warp sequence, we apply, we basically go out in K-space and then perform a readout. So now I want to see what is the effect because we go from this part of K-space, the positive, negative part of K-space to the positive part of K-space. During that time, I mean, actually, spin starts processing and losing coherence immediately after you excite. So during this time, they lose, but we don't collect any signal, right? We don't collect any signal. Then we start collecting signals when we go along the X direction, okay? So we want to understand kind of what is actually going on here and what is the effect on the image. All right, so we did the same trick where you have Kx is a function of T minus TE. What is TE stands for? And because of NMR, it's flipped. Nah, I don't know why they call it TE. It's echo time. Time echo. So where is T? Where does K-space cross? Where at what time point it crosses, or where's T?
When it crosses 0?
Yeah, when actually at this point, when it crosses this point, or when it crosses 0. Okay, that is time equal T. Okay, so then we can represent again time as a function of K-space, and then write the transverse magnetization equation, which is mxy r0 e to the minus I omega error. So this is the error field. E minus T over T2. This is also a function of R, don't forget. And then E minus I 2 pi K T X. Okay, so this is the K-space parts. This is phase due to K-space. And these are decay components, right? Well, I mean, this is the imaginary. So you might also attribute some phase. We'll see to that right, in a second. All right, so we want to analyze this. All right, so if we let's neglect T2 for a second, and then and substitute T into the equation. And let's see what happens. Okay? Let's see what happens. Well, in that case, mxy of R and T is mxy r and 0 e to the minus, this is the error field, and now you've got this, now it's multiplied by some function of K-space. It's a function of K-space, e minus I 2 pi, kx, and so on and so forth. Okay. So what I'm going to do now is I'm going to take a look at this. I have like a I here. I have the I here. This, and then I have T, and I have T. Okay. Now, when this argument doesn't have a T, this is constant, right? So this will multiply T, and it will also multiply this, right? This is a function of time, or K, I guess. This is a function of K. Oh boy, I confused you completely. All right, forget it. Hold on. This is K, and this is K. This is I, and this is I. Now, this argument will multiply by this, and it would also multiply this one, right? So if you think about it, there's a component that actually doesn't depend on K-space. And these two, this one, this multiplication, and this can be kind of joined as a function of K-space, right? This is a function of K, this is a K. So what I'm doing is actually joining them. So from here, is just algebra, I'm going to go and I get mxyr0 e to the minus I omega er te, right? This is the stuff that is not dependent on k-space. And that came by multiplying this by that. And then e minus I 2 pi kx, kx and this kx. And then now I can do x plus omega sub er over gamma gx, right? So this was this component. So basically I took the I 2 pi kx out and then this kind of what I get. All right, any argument with that? Basically, I just rearranged those terms. I rearranged them in a very nice way that it's very helpful. Okay, because this component is what we've seen kind of before, because when we get the signal is the integral kind of, right, like over the entire thing, right? So when we get the signal, this would be basically cause dephasing, right? But also it could cause maybe constant phase. It depends, right? So either some phase or dephasing, depending on the level. We'll see in a second. This part over here, this is pretty much, a Fourier kernel, right? That's the Fourier kernel. But the only difference is now that this is not x, just x. This is x plus some other thing, which I can call it x prime. What does it mean though? If I try to reconstruct an image, then I would have expected the signal to come from position X. But effectively, now I have some error that will result in the image being displaced, because now I have pretty much a new axis. So this part will cause the image to actually reconstruct at a different position, or parts of the image that are inhomogeneous to be reconstructed at a different position. Which in some way kind of makes sense, because if you have a spin that's processing at a slightly different frequency, right? It's very hard to distinguish between a spin that processes in the right frequency, it's off axis, but you have a gradient on, so it's like, it's very different, like they could be the same. So that would basically cause displacement, and this was called dephasing and phasing. Okay, so my point is that on resonance spins, at position X, at position X prime, will produce the same signal as a spin at position X with off resonance. Okay, if you have spins that are actually on resonance, but they're at a different position, will produce the same signal. If they were at this position, will produce exactly the same signal as a spin that is at another position, but with off resonance. So the reconstruction would then take that spin that's supposed to appear at position X and reconstruct it at X prime. That's because you don't know that it's off resonance. If you knew, you could have corrected for it, right? But if you don't know, you don't know. Here's an image that I collected. Oh, by the way, this displacement only happens in the readout direction, right? Because if you think about it, the modulation happens only in this direction. It doesn't happen across the Y direction or across the phasing co-direction. Because when I go from here to here, it's exactly the same time happens. So the same modulation happen in X. And the same modulation, the similar thing that I talked about when we talked about T2. So effectively, it happens only in the X direction. So here's what I did in this experiment. In this experiment, I applied a linear gradient, and then I performed an image. This is supposed to look like a circle. It doesn't look like a circle. What happened here? What happened here? What happened was I applied a certain gradient that created inhomogeneity. All right, it created inhomogeneity. And when I performed imaging, then spins were displaced to a different location because this gradient was on. Now that gradient simulated inhomogeneity. Okay, so the question, so what happened is that if you look at this is supposed to be a circle, but it was sheared. It was sheared because spins here resonated at a different frequency, and so they were displaced up. Spins at this part of the magnet resonated at a lower frequency, so they're displaced down. And the amount of displacement is linear from the center. So that's why you get shearing. The question is, which one is the readout direction? Is the readout direction left, right, or top down?
Left, right.
Left, right. Why?
Because it's shifted in that direction.
Yes, so if I apply an X gradient, that means that the field here will be, if I apply an X gradient, that means that here will be high field, right? Higher field, and here will be lower field, right? So it's exactly the type of thing that you see. So the readout direction is this. No, actually, no, I'm sorry. You're mistaken. I applied an X gradient as a inhomogeneity, but the displacement happened in which direction? The displacement happened
along
here.
the Y direction.
Yeah, so the readout direction is actually this. The displacement happened. You're right in some way that the inhomogeneity is left, right, but the displacement was in the readout direction, which is in this direction. Okay. Now the other thing that you will see here is if we actually look at this image, there's another interesting feature, which is over here. This is supposed to have, the same, this is supposed to be a complete circle. But now there is a signal loss here. There's no signal. And then actually there's other points over here. There's these dots over here too. And there's one over here too. Anybody has an idea why there is a signal loss over there? Let me give you a hint.
Maybe?
Let me give you a hint. This phantom was put as is. This, like, if you actually look at it, this would be the up part, and this would be the bottom part. This lies on the table, and this is the upper part.
Then because of gravity. The water.
Well, gravity has to do something with it, but not with the signal.
Top part is air, not water.
The water
Because
flow.
we saw that in the scan yesterday.
Yes. It's air, but it's not. But the signal is not lost because there's air here. The signal is not because there's a bubble close by. and the bubble is air-water interface, and that causes field inhomogeneity that is so big that you'll get dephasing within a voxel. And so this is, for example, why the signal here is lost, because of air-water interfaces. So you see some signal decay because of that. So there's two phenomena here. One is displacement, and the other one is signal loss that you see. Here's another, that's another effect, actually. That's another effect. This is an image of a breast. I showed you this before, actually. And if you remember, there's this e to the I w sub e of r, right? Times t component, right? That we had for the for the signal. And sorry, TE. Remember this component that we had? And we said that this either causes dephasing or phasing. So this acquisition was done such that at time TE, the water and the lipids were exactly have the same phase. And since they have the same phase, their signal adds together. So if I have a voxel from water, then and a voxel of phase, they will have exactly the same phase. Sorry, a voxel made of water and fat, they both have the same phase, and so they add. This image was acquired when water and fat have actually opposite phase. And what happens when you have opposite phase? You may have complete signal cancellation when the concentration of water and fat at those voxels are equal. And these happen at the boundaries between fat and fat and tissue. And the breast, again, I told you, it has a lot of lipids, and this is a boundary, for example, between lipid and tissue. This is another boundary where fat and water is exactly the same, produce exactly the same signal, and because their phase is opposite, and their signal cancels. Okay. So there is a phase effect. Sometimes that phase would create loss of signal. Sometimes you don't see it, and so on and so forth. It depends on the time that you cross the center of K-space. Okay. The time that you cross the center of K-space will result in different phases because of that. The last one that I want to show you is, this is a brain image. And the subcutaneous fat has a different resonance frequency. And so this is the reason, by the way, it's called chemical shift, because lipids have a lower frequency than water. And because they have a lower frequency of water, they'll be reconstructed at X prime. And so you can kind of see that, basically, it's almost overlapping with the brain, right? It's almost overlapping with the brain. By the way, there's another, soft one here, right? That's another fat peak. Okay, I think from CH3 that you see here, right? There's CH2 and CH3, right? So this fine line here is CH3, which is very interesting. Okay, so it is shifted a little bit. Now, how much shifting? It's not a lot. And the thing is, we can actually reduce this amount of shifting. How do we reduce? Well, that shift depends on GX. If GX is small, then the shift is large. If GX is large, then the shift is small. So if we actually increase the gradient, the readout gradient, then we have less and less shift. Okay, these are 3 images. And in those 3 images, the difference is that this one used a higher gradient than this one. So this has a longer readout. So what does it mean, a higher gradient? A higher gradient means that if I want to go from this part of K-space to this part of K-space, if I have a small gradient, it's going to take me some time to get to the other side. Now apply a very fast gradient. So the readout is going to be short. And so all this dephasing is not going to be significant, right? The amount of phase that you accrue is going to be much less. Okay, that's where it comes from. Any questions? I didn't even get to Spinaco. Okay, so let's see. So let's say that so if you actually look at the equation, right? It's omega E over gamma gx, right? So now what is gamma over 2 pi times gx? That's units of 1 kilohertz per centimeter, right? Let's say, so sorry, gamma over 2 pi times gx, that's a unit of frequency per centimeter, because gx is Gauss per centimeter, and then multiplied by gamma over 2 pi, then you get kilohertz, let's say, over centimeter. And so let's say gamma over 2 pi gx is, let's say, 1 kilohertz per centimeter. So now when I apply a gradient, I will have every centimeter increment of 1 kilohertz. Let's say I have an error field of about 3 ppm. Is that reasonable? Absolutely. 3 ppm all the time. Okay. So that basically means that my angular frequency error is going to be 2 pi times 200 hertz approximately at 1.5 t. Okay. At 1.5 t, that will be approximately 200 hertz, 3 ppm. Okay. So that is the error. I apply 1 kilohertz per centimeter, but now I have an error of about 200 hertz somewhere. So now I want to understand what is really this delta x. Delta x will be x prime, where it will be reconstructed, minus x, where I am actually at r. And so in that case, it will be omega e times r over gamma gx, right? That's pretty much what x prime minus x is. And then if I actually perform the calculation, I will see that the delta x, the displacement in the reconstruction with 3 ppm and 1 kilohertz per centimeter will result in 2 millimeters of displacement. Now, 2 millimeters of displacement, well, I mean, am I going to be able to see it? Well, that depends. If you image at the resolution of 1 millimeter, then it will shift by 2 pixels. If you image at a resolution of a centimeter, you won't be able to see much shift. You see, because it will be subvoxel. So it really depends on your parameters, how much shift you're going to get, and so on and so forth. Okay, but this is how you are able to analyze this. And pretty much what you really want to calculate, it's a notion of what's called bandwidth per pixel. How much, when you apply a gradient, if I apply 1 kilohertz per centimeter, if I have, let's say, 1 voxel and if I have 1 kilohertz per centimeter, I can, based on my resolution, I can figure out what is my bandwidth for every pixel. So 1 kilohertz at 1 millimeter, 1 kilohertz per centimeter at 1 millimeter will result in a bandwidth per pixel of 100 hertz, right? 100 hertz. So each pixel really contains about 100 hertz. of frequencies. And if I have a deviation of 200 hertz, well, then yeah, it could move 2 pixels away. It will move outside of your pixel. So how do I correct it? I can improve my bandwidth per pixel by applying a larger gradient. And so then each pixel will have a higher bandwidth, and so it will not be affected so much by this 200 hertz. Not if you get that concept. Not this way if you don't. Okay, so here are the effect of in spin warp. Off resonance really modeled spatial distortions, just a few pixels in the readout direction. Maybe 2 or 3, but not more than that. Relatively benign artifacts. And you can reduce those artifacts if you apply a large gradient. Now, chemical shift. Chemical shift, fat shifts minus 220 hertz at 1.5T and 440 hertz at 3T. And at 7T, more. Okay. So fat image is displaced from water. In practice, fat water shift is limited to about 2 pixels or so because of the bandwidth per pixel notion. Okay. So 2 pixel shifts are effectively 2 cycles of linear phase across K-space. That's really what it means. If you want to shift by 2, then you need to, if you have K-space, then you need to have kind of 2 cycles of phase across K-space that you accrue to move you by 2 pixels by the shift theorem. It's linear phase pretty much. Linear phase of 2 cycles will shift you 2 pixels. Okay, so 2 cycles for 22 hertz, it's about 9.1 milliseconds. So if you do a readout of 9.1 milliseconds, you'll get 2 pixel shifts. If your readout is shorter, you'll get less shift. Okay, that's another notion. Now here is the problem. The problem comes when you do EPI or echoplanar imaging. In echoplanar imaging, I collect data here. This is maybe 2-3 milliseconds, and then I go down, and then I read another line, and then I read another line, and then I read another line. I guess this one is 1 millisecond, and then there's time between them, right? So there's not a lot of cycles. There's about maybe 0.4 cycles accrued along this direction. So that's very small. But think about how many lines. If I want to acquire a lot of lines, then actually there's no really phase encode direction, but if this is the readout and you go this, then sometimes people call this the phase encode, even though it's not really phase encodes, but it's the long direction. Then there's actually a lot of phase that's being accumulated in this direction. A lot of phase. So that phase would result, and the other thing is that happens is that you accrue phase in this direction, and then you accrue phase in the opposite direction. So there's 2 phenomena that happen. First of all, fat will be shifted. So a Poinsett function, what was a Poinsett function? Again, in order to figure out what the fat image would look like, you take the fat image and you convolve with this Poinsett function, which is the result of this phase. It's the inverse Fourier transform of this phase. Okay, so basically you'll have shift up by this, and then you have this weird thing over here that would create some artifact. And this thing happens because of this back and forth. This big shift is because you accumulate a lot of phase in this direction. I know I'm going a little bit fast, but don't have a lot of choice here. So if this is the Poinsett function, and now I simulated an acquisition of EPI with chemical shift, you're supposed to see this bright thing around this Sheplogin phantom, but now it's going to be shifted down. And then there's going to be this like tiny artifact because of this effect. Okay, so this is an EPI image. Very typical API image when you have fat. This is a leg. This is my leg. My leg has some fat around it. But turns out, because I broke my leg, the fat is now not in the right position. It moved. No, this is because of the acquisition. It's not because of, the fat is actually in the right position, but because of chemical shift, it moved. It moved so much. Look how much it moved. And then I have this small weird thing here that happens, and that's because of this. Okay, but this is the really main effect. Fat will shift down. And in EPI is a significant shift. So if you do EPI imaging around fat, you have to do fat suppression. Otherwise, it's going to overlap on your image and it's going to mess it up. Think about EPI in the abdomen. I mean, like you won't be able to see anything. Fat would just like overlap with all sorts of stuff. Okay. Now, spiral, that's an interesting thing. So the phase, when you do a spiral, the phase starts accumulating along the spiral. It's not now phase from top to bottom or left to right. It's more angular. And so the Poinsot function actually looks, something. Yeah. So the Poinsot function it will be different. And so this is the Poinsot function for a 2 millisecond readout. It's pretty nice. And the image that you get is quite nice. If you actually have a longer readout of 5 milliseconds, then now the Poinsot function starts spreading because you have more phase. So what you get actually is a blur of the fat. And if you read out for 13 milliseconds, then the fat will blur significantly. So it's not displaced, it's blurred. And that's because we're doing a different readout. So it really depends on how you collect data. What is the effect of off resonance? Here's the same phantom. Now I apply again the same gradient and I collected the spiral image. What happened with 2DFT? You got shearing, right? A shearing artifact. I showed you before. Now, what you get is blurring. And you see that where you're off resonance, it's very blurred. Here in the middle, not a lot of off resonance because I applied a gradient. Gradient in the middle doesn't do anything. So now it's sharp. And on the left side, again, off resonance. And as you go further away, it's more blurred. Is this a problem? Ekin, is this a problem?
Unfortunately, yeah.
Is this a problem to you? Is this a problem that you're having?
Yeah, it's a big problem. Yeah.
It's a big problem. Did we record?
Yeah.
Okay. Almost having a heart attack. All right, I'm going to quickly go over this in 5 minutes. I'm going to steal 5 minutes because we have to do, I have to at least give you some idea of what it is because you're going to see it, some of you are going to see it tomorrow. Let's talk about echoes. So early in NMR, people noticed the following odd behavior. This is, by the way, Erwin Hahn. Erwin Hahn, Berkeley faculty, he discovered this phenomenon. Okay. What he did, he applied a 90-degree excitation and another 90-degree excitation. And so what happened? After the first excitation, you get some FID. After the second excitation, you start getting FID, and suddenly the signal goes up. Oh, hold on. What is going on? How come the signal goes up? It's supposed to decay, but it goes up and then decays. So strange. So he figured it out. And he wrote a paper and created the notion of spin echo. Got very famous for it. Often they're called actually Hahn echoes, by the way, because of him. So he did it for a 1990, but actually the phenomena is more significant when you do a 90 and then a 180 degree. And I want to show you what happens. Okay. So let's look at those spins. Now you have a lot of isochromats at MZ, right? They're oriented along the main magnetic field. And now I'm exciting a 90 degree. Before I have no excitation, and immediately after I excite, and then I start getting T2 star decay because the spin starts spreading. Okay, then, uh-oh, I already flipped the pancake, huh? I was supposed to, okay. So then what happens, they start spreading and spreading and spreading, and I'm losing signal till I get just before the 180. Now, what does the 180 does? It flips the spins, right? So here's the 90, the spins dephase, and then there comes the 180, and this whole pancake flips. Okay? Now, what do the spins do after that? Let me do it again. Remember, red spins rotate clockwise. Blue spins rotate counterclockwise, right? The pancake is flipped, but now the spins still precess. You know, red spins precess clockwise. Blue spins precess counterclockwise. So they keep precessing. Oh, actually, I did this. Anyway, so this is what happened. It flips, and then the spins keeps precessing. But then look what happened. There is a single point in time where those spins come back and rephase. And that is called a hand echo or a spin echo. So our signal in the beginning starts dephasing with T2 star, lost. Then the 180 comes, and then the spin starts rephasing. And then at some point, the signal actually goes up. Now, the thing is, the spins also start decaying with T2. So when it goes up, it rises with the T2 star curve, but up to where T2 would have been. And then they still decay with T2 star after that. But this is called an echo. And it refocuses those spins. So any signal loss, due to dephasing is actually recovered by the spin echo. Okay. Now, I'm not going to go more than that. We'll talk about more about spin echo next. But the idea here is you do a 90, then a 180, and then at exactly, if this is what we call TE or the echo time, then here is TE over 2, and here is TE over 2. So if this is the distance between the spin echo, TE over 2, and the 90 degree, then at another TE over 2 after that, you'll start seeing the signal pop up again. And folks, you will see this. You will see this in the lab. Because we are going to implement, we're going to give you a pulse acquire, and then you're going to add a spin echo, and then you're going to add slice select, and you're going to add phasing codes and readout, and you're going to create images. I mean, it's going to be legendary, but you're going to be able to see this. You're going to see the nice spin echo that comes out of it. Okay. So huge thing, because really there's no way to image T2 because T2 is always mixed with T2 star. But using a spin echo, suddenly for a short amount of time, you actually get the right T2 weighting that you may be interested in and not dominated by T2 star. I'll stop here because I already stole a lot of minutes from you. And I apologize for this, but I'm faculty and we are just privileged. Yeah, but I really wanted you to see this before we do the lab. So tell your friends to watch the videos if they missed this lecture. Thank you very much. Have a great weekend. Great weekend. And I'll see you all on Tuesday. Bye, everyone.